Hello, hello, and welcome to your next session. It is my pleasure to introduce our next speaker. Next up, we have Enrico Santus, and he is the Senior Data Scientist at Bayer Pharmaceuticals. And today his talk is entitled Natural Language Processing, Challenges and Opportunities in Healthcare. So please welcome to our virtual stage, Enrico. You can come on out and join us with your camera and your slides. Hi, Enrico.
Hi, Morgan. Hi, everyone.
Okay, great. So I'm just going to turn off my camera here and you can share your slides and take it away.
Sounds great. Can you see? Thank you, everyone. Today I'm going to talk about natural language processing, challenges and opportunities in healthcare. Making a decision is about taking one way or another. It is estimated that human adults take about 35,000 decisions per day. Of course, the majority of them are about what to eat, what to wear, how long to exercise, and so on. But we are talking about over 1 million decisions per month. So the question is, how would we look like if we were going to take all of them wrong? Of course, all joking aside, the issue of making the right decision is one of the major concerns in the industries today. And if in some domains these decisions may affect the revenue, in some others, like in the healthcare domain, they affect human life. We can see this every day with the COVID-19 crisis. Those countries that have adopted the right protocols have came out earlier from the crisis, and eventually they have saved human lives. And by the way, thanks to all the frontliners that have helped us in these difficult months. Making the right decisions requires to have the right information. Studies have demonstrated that failure is 4 times more likely if we take uninformed decisions, regardless of the nature of the decision itself. Succeeding in business means to go towards the goal. And to go towards a goal, not knowing the direction, requires to have a map that gives us the way, the information to get to the goal. And a map like the one that you see in the slide is definitely not the map that will help you to reach the goal. Most likely, you will never be able to reach it with such a map. But if you have a little bit more of information, maybe you can get to the goal. Unfortunately, this map is not very clear, so it's very likely that you're gonna lose your way, and maybe you're gonna lose time, resources, energy, but at the end, probably you will make it. The best case scenario is if you have a map like this one. In this map, you can actually have all the necessary information to get right to the goal. Similarly, in business and in every kind of industry, you may utilize historical patterns to somehow identify trends, insights, and utilize them to predict the outcomes and eventually generate actionable knowledge. This is possible today thanks to the availability of big data. Big data is characterized by velocity. Velocity in the sense that we are producing very quickly big amount of data. 90% of the data has been produced in the last 2 years with a growth of 50 times between 2010 and 2020. Just to give you an example, we are producing 2.9 million emails per second, 20 hours of YouTube videos per minute, and 50 million of tweets per day. And of course, with such a huge generation of data, we are going to have a big volume of big data. We are passing from 4.4 zettabytes in 2013 to 44 zettabytes in 2020. And if we were to save all this data into tablets, like an iPad or something like that, we would need 6.6 stacks of tablets that could reach the moon from the Earth. But given this huge amount of data, are we actually utilizing it? Are we actually exploiting it? Well, the answer is no. According to a report by McKinsey in 2017, 90% of the business decisions are still made on the basis of education, instinct, and gut feeling. Similarly, another report from PwC in 2016 says that 2/3 of the healthcare decisions are rarely or not at all based on data. The reason is that whenever we think about big data, we think about something like that. We see charts, we see tables, we see a lot of numbers. But the reality is that big data looks much more like this. And with such data, you can imagine it's impossible to get any insight. We are at the paradox of being overloaded with data, but yet uninformed. And the reason is that on top of velocity and volume, big data is characterized by the fact that it comes from many sources. And these many sources are not interoperable, and they are not aggregated, and the majority of them are unstructured. Unstructured because they are produced, for example, by people to people, and by people to machines, or machines to people. And people don't speak through tables, they speak natural language. Another big problem for utilizing this data is the veracity of this data. We know that this data contains a lot of biases that overrepresent some classes rather than others, contains noise, such that some signals are hidden in the middle of the noise, and it contains anomalies, sometimes even malicious anomalies, like the fake news in the news domain. Poor data quality is a huge cost for the United States. It is estimated by IBM that is a $3.1 trillion cost per year. So given all this information, now you understand why the available data is growing in an exponential way, and our capability of utilizing it is growing in a linear way, creating a huge gap that is going to be larger and larger with the years. If we look at the healthcare data in particular, we see that 80% of it is unstructured. And being unstructured is untapped after its creation. What does it mean? It means that the only time in which this data is used again is when a patient goes to the doctor and asks the doctor to look into it. And generally, even in this case, doctors are unable to find the relevant information into this data. In fact, 65% of providers have complained that they are unable to utilize the patient data when they need it at the time of the encounter. On the population level, this is also a big loss in information. In fact, we have millions of EHRs, insurance claims, radiological images, voice recordings, and this data is sitting there without being used. Inside there are socioeconomic information, patient medical histories, diagnoses, treatments, genetic information that are there for the benefit of none. So when we have a problem in the healthcare domain, what we should do is to try to look into the data that is available. We said 80% of it is unstructured. So the first thing we should do is to turn it into structured data and make it interoperable and aggregated with all the other structured data that we have. And after that, try to gain some insights. Insights that can turn into actionable knowledge, which can turn finally into actions. But why, how can we do that? We can do it with utilizing, of course, humans, but humans are an outdated technology in this respect. They can read maximum 1,000 words per minute with 85% understanding, meaning that if they were to read the full big data amount of big data volume, we would take ages. And that's the reason why, according to Cancer Link Q, as of today, all clinical decisions are taken on the basis of 3% of the population that participated in clinical trials. This means that we are leaving outside of our decisions 97% of the population. It is somehow like looking at Mona Lisa and trying to appreciate it by looking only at the left side picture. Of course, this is not possible. So what other options do we have? Well, there is one that is called natural language processing. It's an emerging technique that has recently made a lot of news, and it's a subfield of artificial intelligence that manipulates, understand, and generate human language in order to solve a number of problems, leveraging, of course, on machine learning and deep learning techniques. In the last years, between MIT and Bayer, I have mostly worked on its application to problems related to healthcare and pharma. And in particular, I have worked on turning hard copies document into digital document, for example, using optical character recognition techniques. And I've worked on organizing these documents according to some criteria into categories. I work into identifying important information inside these documents and turn this information into the form of tables, which can be analyzed through simple analytical instruments, even in Excel or whatever other software. And I also try to identify, retrieve evidence to either support or refute the information that was, the relevant information that was collected from these documents. And finally, I have utilized all this information once it was proved that it was efficient to perform clinical tasks, such as predicting the risk or selecting the patients for a procedure or other kind of. In the first use case that I want to talk about. In 2019, in a collaborative work between MIT and MGH, we developed a convolutional neural network to extract information from 25,000 breast pathology reports originated in 7 hospitals. The breast pathology reports are notes that are written by pathologists in the form of free text. And inside them, there is buried information about the location or the histology of the tumor. Our goal was twofold. On the one side, we wanted to create a system that could perform better than the commonly utilized rule-based approach. And on the other end, we wanted to explore whether this system was somehow applicable to a number of institutions, rather than only the institutions on which it was trained. In fact, as you probably know, every single institution has its own way to create data. And the variance between the various institutions create problems in the performance of the system. So we want to measure these problems and see whether the CNNs were able to generalize. So you see here, we have a report in the form of narrative, as you see on the left. It's an unstructured document, and we want to turn in something structured, as you see on the right. Basically, we identified the several attributes, and for each attribute, we had to select whether they were present or absent. We access to, as I said, 25,000 reports from 7 hospitals, 5 of them in Boston, 1 of them in Detroit, and 1 of them in Pakistan. And we had a population of about 56 years old that got visited between 1987 and 2017. The majority of this population was white, 77%, while the other ethnicities were represented by 2 to 4%. And almost all of them were women. As you can see, the system works in this way. You had a report. This report is turned into a matrix of word embeddings. Every word embedding is basically a vector containing float numbers representing the meaning of that word. And then we pass this matrix representing the report into the convolutional neural network, which has a convolutional layer that tries to identify patterns. Then you have the max over time pooling layer that tries to summarize what the first layer is identified. And finally, the softmax that returns you a probability, which can be whether the attribute was present or absent, or the location was left or right. And here we see the results. We have 2 plots. On the left side is the plot of the accuracy over the known institution. On the right side, accuracy over the unknown institutions, meaning the institutions that were not present in the training set. You see that the maximum accuracy with 5,500 training examples was about 96%, which is very accurate. It's more accurate than humans sometimes. And what you see on the left is that you have three lines. These 3 lines represent 3 settings of the same system. CNN1, CNN2, and CNN4, where 1, 2, and 4 represent how many institutions the system was trained on. And you can see that on the left side, the 3 settings perform basically the same way, with the CNN4 that takes a little bit more time to reach the best performance. This is because it has to deal with higher variability, because it's trained on 4 institutions, right? Similarly, you see the same issue on the right side. The CNN4 takes a little bit longer. But one thing very interesting that you can see is that the system trained on one single institution is not very able to generalize to new institutions. In fact, the performance there is about 93%. While the system trained on 4 institutions is much better in generalizing on new institutions. And it reaches an accuracy of about 96%, 94, 96%. So our goal was to provide physicians with a tool for quickly extracting useful information from narrative and utilize this information for retrospective studies. Until our system was out, most of the studies were trying to study the breast cancer on top of 300 and 600 cases, as you can see here on the left. But of course, this can give you a very clear picture of the phenomenon you are studying. Thanks to our system, physicians in MGH could actually do studies with 6,000 cases, which can provide you a very fine-grained understanding of the problem at hand. We also generalized the system in order to address different organs like brain, lung, pancreas, prostate, and so on. And now let's go to the next use case that I want to talk about. It's improving patient selection for cardiac resynchronization therapy. So the CRT is a therapy that is well known for helping patients with heart failure, somehow to reduce the hospitalizations and improve the survival. But unfortunately, it's a very expensive procedure, and it's also highly risky. And not everyone benefits from it. So identifying the people that don't benefit from it could be a very important service to improve their life. So in fact, from the literature, we discovered that 1/3 of the patients that go through this procedure actually don't benefit out of it. And not at least within 18 months from the procedure. And a subgroup of them, unfortunately, even dies for comorbidities and so on. In this case, the collaboration was with Dana-Farber. We collected 990 CRT patients that were visited between 2004 and 2015. Each of them had about 75 nodes. We checked the mean left ventricular ejection fraction, which was 24.8. This is kind of improvement. And in fact, we evaluate the reduced benefit as less than 0% improvement in the left LVEF, sorry. And or also in the death within 18 months. So these people basically didn't benefit from the procedure. And these people counted to 403 out of 990, meaning 40% of the patients had a reduced benefit, 25% with no improvement, 15% unfortunately died. The average age of the patients was 71 years old, 87% were white, 78% of them were male. In this case, we had to utilize a lot of information. Some of it was structured already, some of it was unstructured. The information we utilized was the demographics, the past health service utilization, the billing codes, the encounter information like type, length of stay, and so on, laboratory values, medications, clinical information, and finally, the EHR narrative. And
sorry, your quick 5-minute warning. Go ahead.
Thank you.
Okay.
And we had to utilize all this information, aggregate it all together, and finally exploit it for the patient selection that was the actionable knowledge we wanted at the end. Let's see a little bit the system we created. We split, of course, the patient 80% for training, 20% for testing. We train 4 classifiers: logistic regression, support vector machine, random forest, and extreme gradient boosting. And the latest was the one that performed the best. And actually, we tuned the hyperparameters, of course, on the validation set to improve the F-beta score with 3-cross validation. The MES model was run then on the LDAO test set. And we obtained some interesting results. You can see them in the picture on the right, but what is important is that basically we have identified 26% of the patients that had reduced benefit with an accuracy, with actually precision of 79%. So you can see here in the picture, the pink patients that you identify there are those that have gone through the procedure and didn't benefit from it, and our system could predict it. So that's what NLP kind of enables. Conclusions. I don't have any conclusion. We have just started this adventure. NLP is a technique that is helping the healthcare since a few years, and it's getting very, very interesting results. What is interesting is that the US spends about 18%, 18% of the GDP on the healthcare, and this amounts to $3.7 trillion, which is about $10,000 for every single citizen. And this is a huge cost that can be reduced with the utilization of such techniques. There are a lot of things that NLP promises. So some of them are speeding the process, making it efficient, making it effective, and also increasing the humanity in the healthcare system. Actually, in a certain sense, it also means to turn healthcare from being focused on the care to be focused on the health of the patient. And how can this happen? It can happen by cutting costs through improved care coordination, for example, reducing the unnecessary service utilization, preventing chronic diseases, allocating efficiently the internal resources. Or it can be done by improving the monitoring of the patients, also in situations that are not considered in the traditional environment, like medication adherence management, home-based monitoring, and improving also the patient-provider interactions while increasing the patient literacy. One more thing that NLP enables is the precision medicine, which utilizes massive amounts of data, of big data, to tailor individual treatments. And this is the next step that is being prepared by this technology. So given this all, we shouldn't be surprised that the global NLP market is growing at a compound annual growth rate of 20.5%. In 2020 is 1.5 billions of USD dollars, and is likely in 5 years to reach 3.7 billions, with the United States leading this process. The COVID-19.
1 minute warning.
Thank you. I'm really about to close. And the COVID-19 has speeded up this process, has accelerated this process pretty much. But actually, we are still too late. If these technologies were available in the beginning of this year, in January, now probably 2020 could have been a totally different year. Thank you.
Okay, great. That was wonderful. Thank you so much. If you could unshare your screen and turn off your camera for a moment.
Sure.
And everyone, please give Enrico a warm virtual round of applause, and hope you all enjoyed. Have a great time.
Thank you.